reading this.
All right. Well, all right. So Graham put 10th of January, and so I had that in my head, and then so it's a good thing that I had actually made some notes yesterday, because it is today the 9th by my clock, which is the only clock that's important. All right, so I was going to have more sort of background information, but I think everybody here at least understands what the problem is, and if not, I can kind of bring up browser to talk about it, or bring up a session and show like Rebel 2 messing it up. But everyone here kind of knows what the problem is, that historical Rebel has this concept of binding where you connect words to contexts. If something is evaluating them and it runs get, or then it expects to look up that word in that context, and wherever you pass that block around to, it's supposed to be able to keep that. And the fact that it does keep that is why you can run a block that kind of came from another function, was built in another function, refers to values that are local to that function, and yet that function that receives this block executes it with the glued on pointers that block had. That's why if can run the block that you give it, even though that block contains variables that are local to the function calling if, not to if. And that's a very fundamental aspect of an expectation that to make Rebel work. And yet there were so many different ways in which this fundamental concept had not been really explained. It was just kind of taken for granted. And so there are all these black holes that has been really the purpose of a number of changes in Ren-C to fix. And virtual binding is just based on this idea that you want to be able to have a block that doesn't necessarily belong to you, and or the user doesn't think of that block as being something that is being passed to something that's going to mutate it. There's some operations that, like append, where you expect it to be mutating the block that it takes in. And an issue with binding is that since there was no sort of concept of binding besides manipulating the pointers that are resident in the words that are in blocks, the only way that you could ever affect binding historical Rebel to change it would be to mutate it, or you make a copy and give the copy the new binding. And you see some examples, like if you pass a body block into a function, the function would make a copy of that block and then bind the local variables and arguments to the function, but it would not change the bindings of the block you passed in. And that's because it made a copy, and there are reasons why it makes a copy other than that. So as long as it was making a copy, it went ahead and changed it. But some things didn't make a copy, like when you make an object and you pass it a block. It didn't have a reason to make a copy of that code, and so it would just change the bindings on that, for all the words in that block. And another case would be the for eaches and the use. It would change the bindings of the blocks it was given, and that's not always what you want. And one of the things about some recent changes I made inside the code was that it respects constness. So when you pass around values and arrays, we know whether or not you have asked whether that array is mutable or not. And failure to check that bit, if you remember protect from R3 alpha, the idea you could say, like, hey, I want to protect this object from being changed. You could apply that bit, but any place that didn't check it would change it. And so there'd be these bugs that would be filed rather often whenever anyone would test it, to notice that most places in the system were not heeding that bit, or many places were not heeding that bit. And so you can just sort of piecewise go in, you can go, oh, well, all right, well, when we extract this array from that block, we will remember, since this is a mutating operation, we'll remember to check it. But remembering to check it is a very, that's sporadic. It's just waiting for the next time someone has an operation that doesn't check. And so I sort of systemically have redone it in a way that's relatively low invasive. I mean, some of the changes here the goal is to make it so the code still looks like and runs like ordinary C. And that it doesn't rely on C++. But we can use C++ in some ways to check conditions, and some manipulations using C++ was applied to check and catch cases when things didn't have mutable, they hadn't checked for protection yet as to whether it was okay to modify a block or not. And so if you haven't done that check, it would tell you, hey, you physically, at compile time, it won't compile the code for the interpreter if you don't check and then use that check to transition over to say, okay, now I have a mutable pointer. And binding, it reveals places in the code that was doing this, where it, the function had a array that it had not checked for mutability on, and whether you have mutability or not, sometimes you might not. And make object would be one of these, that block that it would take. It would say, okay, give me the array. Okay, now we're going to run it. But it didn't. But then if that gets passed to bind, then we catch the fact that it was mutating it. So catching all these places in the code sort of shows you where these violations were, and you can see how those violations would be bad if you have constructed a parse rule, let's say, and you gave it very specific bindings to the variables you meant, and then you pass that through and it gets composed somewhere, and you make an object and the block is in it and the bindings are changed. You didn't necessarily expect that, but this would catch it. So all that exposition aside here, let's look at how we might be able to, what are the ground rules for being able to have binding information travel along with a block and yet not have to mutate it. So in the case of a for each or a use or whatever, they've in R3 alpha and Rebel 2, a small object is created that just holds the name y and the variable, a slot for whatever variable value that holds. And historically, what it would do is it would walk through the body and look for any instances of the term y and mutably change that word to point to that object, destroying whatever it had pointed to before. So the concept we have here is to instead, every time you pass around a block like this, so I have my cursor here, every time you pass to this do, this is all pseudocode, right? You call something that's going to do an array, you don't just pass the cell of the array, but you also pass along a patch, which is the head of a linked list of virtual binding information. It's more complicated than that, but let's just think of it that way. And so here I'm just kind of showing these steps. You make your little object, you make a patch that refers to that object, and then when you run the execution, you pass in the patch as well as the body. Now it's not quite like that. Well, okay, here I mentioned the fact that it is central to the idea that is actually a const body. This means that the C compiler will enforce that the data that lives in that cell, those 4 platform pointers, we've talked about that before, that none of those 4 platform pointers can be changed. So if it were a block, you couldn't change the index. If it were an array, you couldn't change what the series was it points to. If it's a, this isn't to be confused with that the actual data is const. Like the series may be itself mutable, but this is just saying that cell itself can't be changed. And that's where the binding pointer lives. So we don't change that. But another thing that came up kind of when I was reasoning about how to make this work with any level of efficiency, this efficiency depends on caching. If we loop through something 10,000 times, and that has with a virtual bind on it, you have to look up every word in that block at some point to determine whether it's a candidate for that virtual bind or whether it's a miss. So You don't know in advance when you're looking at that body, you see print, you don't know that it's not something that's being overridden by the virtual bind. You don't have any way to really a priori know that print isn't and X is. We don't have a discernment of things that can and can't be overridden in Rebel. Everything's equal, right? So we have to do some level of caching to make this efficient. So that word's going to have to store and remember where in the patch it found, whether it found, whether it found it in the virtual binding patch chain or not, and B, where it found it. So if it caches that information, that means it expects to trust it the next time it goes through the loop and sees it again. And if you were allowed to expand the objects and expect those expansions to take effect, you couldn't reliably trust the information that was in it. You would have to kind of somehow expire all the virtual binding patches that refer to a given object, and you wouldn't know which of the things that you looked up were before the expiration or after the expiration. So you have to timestamp them or something. And so in order to not end up in an unpredictable situation where some of the caches will find it and some of them won't, the patch, the virtual binding patch has to remember how many things were in that object. Remember, you can only append objects. You can't delete things. So that's going to be enough. You just have to know what was the length, and then the patch only applies up to that length. And that's not too crazy, right? Because if you did a mutable bind, the mutable bind wouldn't see anything that you added to that object after the bind operation. So that's really the same property there. But it's important because if we didn't do that, then you'd have these untrustworthy caches that sometimes would find the variable or not. So you could loop over things and it would just give you different results. So other thing is, to flesh out the fact that, of what's going on here, that patch has to inherit any patches that were already in effect. So you don't just, you have to link these new patches into the chain where they take on any existing ones. So if you have a for each inside of a for each, inside of a make object, inside of a use, your chains can get kind of long, right? But they tend to be pretty shallow. Oddly enough, they're not that bad so far, in practice. And how big is a patch? And how complicated is this? And how do we reuse as much of what we already have in terms of garbage collection mechanics and linking and all that? Well, what I did is I made these patches use the same tracking nodes as a series, so arrays and strings and all that. And I explained this in my talk about how it's laid out in a way that gives you a content area that if you're, if you have a small series, you don't pay the cost that you would pay for the tracking information of an allocation. You actually put the series data in the node, and that's to help conserve on space for small series. And one of those small series cases that's optimized is a small array. So it's exactly big enough to hold one array cell. And then you can fit however much of a string or whatever else that could fit on your platform to hold a value cell. So what the virtual binding does is it puts a word in that single cell. So you can think of it as an array that contains exactly one value, and it's a word, and it's bound to the last item in the object that was being virtually bound. So I had mentioned that we need to know how long, what the length of the input object was, so that we don't have non-viable numbers in our caches that can't be trusted. And why use a word? Why not a custom structure? Because the more that we put reuse things that we already have, then the garbage collector already knows how to mark it, right? We're reducing the total amount of code. So that's kind of why it uses a word. And then the object obviously is then the binding of that word. So that's the object that you're virtually binding. The word index is how far in that object that you want. And then there's a little bit more information there. as well as whether it's a set word or a regular word that instructs us as to what things to take effect for in the bind. So things like specialize, they only bind the set word in the code block, the words that you're assigning. So you can have a value of that name outside the block, and then you can reference that inside the specialization data, even if it collides with the names inside the thing you're specializing, and that's pretty helpful. So the type of the cell is also heated, and we'll have other kinds of virtual binds. We're going to have virtual unbinds to remove bindings as well. It's a linked list, so the link we have a node pointer to the lower priority patch. So that's going to be another one of these patches, but it actually terminates not necessarily in a patch, but it can also terminate in a frame. That's a whole nother explanation of how relative binding is integrated with this, but I'm trying to keep this as simple as possible. And we have another link, which is a circularly linked list of these virtual binds that of the same to the same object, and this lets us keep track of variations that have a different link, because when you're building these chains, sometimes you'll have something in your hand and you'll chain it to something, and then you'll be in a loop and you'll go and you'll chain something else. You'll build the exact same linked list without knowing it. And what this circularly linked list does is it lets the virtual binding chain look at the time when you say, hey, make me a chain and tack this onto something. It can look through that list and say, well, have I already done this? Because if you have, then you don't have to copy it, and you cut down the number of heap nodes. We're pretty willing to trade off CPU cycles in local environments for not making more GC nodes to track, because that's kind of like where one of our big Achilles heel points is just when we make too many of these nodes. We could burn cycles, but we just pay a lot to have a lot of nodes floating around. So that's an important optimization. Yeah, and here I mentioned that just to give a concrete instance where you make an object, you have two different virtual bind chains. Making different binding chains also has another bad consequence, which is that since they have different identities, you might think that you looked up things differently for those words. So it could be a problem there too. But this is just showing you a case that would be redundant. You have these two blocks that are getting composed into a for each, and if it weren't for that recognition, if these Y if the Y virtual bind patch didn't store that circularly linked list to the other ones, it wouldn't notice that these were the same virtual bind. So that's good. And now onto the caching. I mention often that the rule of the game, this is kind of the game that was set up, is that cells are for platform pointers done like this. This is sort of a premise. It's very hard to imagine changing this rule and really having the same system. And the old way of thinking of a word cell is that its header would say it is a word, and we now have this thing called a heart byte, which also would say it's a word. We can play with these bits a little bit, but some things, like I've mentioned how we now have paths that look like refinements. They say path in their kind, but then their heart says that they're a word, which means that they don't have an array pointer. So anyway, the header is, for instance, a word if we're doing this binding. Historically, the binding would be to either the context or frame or whatever, or null if it's unbound. We'd always keep a spelling pointer to this precise spelling for that word. And then if the word was bound, we'd have the index to which slot in the context it was taking up. Otherwise, it was unused, and generally just 0 for debugging to know that it was unbounded. And the new idea is that we needed space. We need space enough inside of a word cell that we can have some memory of a virtual bind. So what happened is that unbound words point to their spelling. So they're bound to their spelling, basically. And then once you bind it, the context pointer plus the index in the context are used to find the spelling. And that introduced this issue that I mentioned about how, that means you can't have a different spelling at the reference than there is in the context, which introduces this question of how do we reconcile that with our interests in both case preservation and case sensitivity. There's a lot, that's a big topic. We should talk about it and figure out where people's sacred cows are, if any. Mark obviously seems to have a very big sacred cow. He's having a big sacred cow. And so we can talk about that. But just to get this moving, a bound word gives up the unique spelling knowledge to get that knowledge out of the context it is bound to. And then we have some space. We had to chew a little bit of space out here from the index. It's what I call the mondex, actually. It's a modular index to say where it found the thing in the virtual bind chain modulo 4095. And then it caches the last virtual bind chain that it looked this word up in, which we are hoping is going to be most useful for seeing it again. So the theory is that you won't have a lot of contention, that in practice you won't see code being run with one virtual bind, run through one virtual binding view, and then run through another virtual binding view, and then go back to it. So here we see a case where we have two different views of this code, which is foo plus 10. Inside of this one object, it's been composed to see x as 1, and the other it's x as 2. So we haven't actually mutated. Remember, we're not mutating anything of the original code. That code sees foo however it was, and or that's supposed to be x, actually. So so here we are looping 100,000 times using the view as seen by object 1. It caches the first time and then reuses it every time thereafter. So the first time would be a little slower, you would say, and then after that, it just treats it as a normal binding. Obviously, these are small objects, so it's not that big a deal either way. Bigger deal with larger objects. Bad case would be the same thing, except you are flipping back and forth. So it's here we run through one view, and then we run through the other view, and then we run through one view and then the other view. And so the virtual bind information that it cached is not reusable. It looks and it says, hey, the pointer, virtual bind chain pointer that we cached in the cell is not the one we're looking for now. We can't use the information. So that's bad. However, important to know is that, I guess I didn't finish. Yeah, I did finish. If you copy code, then at that point, all the virtual, whatever view is in effect of a virtual bind at the time that you copy, that's the view that you get. So the new block that you create, that you have, that's mutable, you can apply whatever binding to you want, and the bindings that are on it don't suffer the speed issue of being any slower from virtual bind, because the virtual binds are all go away. So if you ever find a situation where the virtual binding isn't working out for you, you can make a copy. And what's nice about this, I think, is that unlike in Rebel 2 and R3 Alpha and Red, where you kind of didn't know, things are modifying the bindings out from under you, virtual binds come back with a const value. You can ask for it mutably, but you have to know the risks of what you're going to see if you get a mutable view on it. But at least it warns you, that you're dealing with a shared view of data, and then you make the decision to copy or not yourself. If we made too many decisions about copying inside the core when you didn't ask to copy, then that has its own consequences besides just taking up more space. Yeah, and I think Chris filed a bug a while ago, which was pointing out something that had happened about protect status changing when you put something in the body of a loop. And people don't really notice or know that R3 alpha and Rebel 2 code makes copies of the loop bodies and for each because it has to bind to those variables, and that's the only way it can do it without corrupting them. So it's just sort of a thing to know. All right. If you're still there, I didn't hear anything, so now you're still there. There you are. So that's just a general overview of it. Any specific questions?
I don't have any questions.
Okay.
It's very impressive. And as always, anytime I see the commas in the code, I think, oh, now Rebel is beautiful.
I think it certainly does improve slides, because you're looking for that economy of space to put a little bit of code, and that applies to when you're writing it as well. And yeah, I think commas are a win.
So just remind me, how does this virtual binding affect case sensitivity now?
Case sensitivity comparison. What it's doing right now is its bindings are case sensitive, but then everything else that did lookups is still, like if you path pick or whatever, it's doing it case insensitively. But that means that if you use multiple cases of the same thing, you will just get the first thing it happens to hit. And we don't do that with maps. The answer with maps was to be case preserving in the keys. But then if you ask for something that has duplicate keys, multiple casings of the same key, it will tell you when you do the select. It'll say, hey, there's multiple cases of that item. You have to use select case. It could arguably apply at the moment that you have to any collection that has case collisions. It could require you to make any selects out of it use case sensitive selects. Just say like, hey, this has been contaminated with multiple cases of the same key. I think the object should at the very least error if you don't use a case sensitive selector when it notices that there are two keys. But because keys and objects aren't hashed the way they are in maps, we don't have that answer at hand particularly fast. We would have to, whenever you did an append, it would have to kind of walk over the keys and make a note to say, oh, this to link the synonyms. So yeah, currently all the main thing is that if you use capital letters or whatever to access something that was defined with lowercase, it won't find it. The only things that I really changed to have a capital variation was like CR and LF. I said, oh, well, so I made capital CR and capital LF. But other than that, so I think there are a number. It's not impossible to imagine ways to still get benefit. I mean, we could sacrifice we can move bits around if it's very, very important to say that binding is case insensitive, but I've had a hard time justifying it. And it's also pretty big, when you say you're making a very flexible programming language, and you're taking huge identifiers away from people who might want to use case as a way to sort of expand the scope of English identifiers that they have for some domain purpose. I think we all agree. I mean, as much as Mark was trying to argue that, well, SQL is case insensitive, or that it's something that you want to see in dialects. Some dialects want to be case insensitive. By the same notion, we're case preserving because some situations are case sensitive. And so saying that the whole language proper needs to, obey its binding rule according to something that you might want to use in a specific context for a dialect, I don't know if that's true. It may be the more flexible thing is to be case sensitive in the language itself for binding, and then provide tools to make it easier for people who want to build structures that are assistive for looking up interpretation of case insensitive situations. Make sure that's there to make it easy for them, and to be involved in all these hard problems of international casing so that people aren't on their own reinventing it every time. That's fine. But for now, just making some headway on because if we didn't sacrifice some bits in the cell, we'd have to go pretty far away from the cell every time, even to some side structure to remember where we looked it up last. And so chewing out those bits is valuable. And I don't know. I mean, it seems a good solution for me. And as far as in the way that I use Rebel, I kind of prefer the case sensitivity a bit, just in terms of standardizing. If we get more standardization of that, because things like that header issue I was pointing to about inheriting the header and then it didn't pay attention to what you said. I don't like those little mysterious things, and I prefer it to be, I think I just prefer it to raise errors more. Like I say, when you look when you do a case insensitive search and there's case duplicates, I feel like storing information to know they're there and erroring and saying, hey, you need to be explicit is more favorable to me than throwing away information when you think you had it, and that happens all the time inside the implementation. You go, like, it happened to me, right? Like I thought, the spelling, we already have that. And I had to get actually pretty far into the implementation before I found a case. I'd gotten a bunch of it running before I realized, oh no, that's lossy. I just lost information. And those kinds of realizations will hit you every time that you're using case insensitive, a system that goes around doing case insensitive stuff behind your back and saying, yeah, I got this. Yeah, you don't got it later because you realize you lost information that was important to you. And so, as I say, the implementation itself being a bit of a cautionary tale on that front, because I didn't even know, and I use it all the time and mess with it all the time, and it didn't even occur to me that I was throwing out a casing when I was writing the first draft of it. So I had to hit an error going, and I'm like, oh, that's right. So whether you think the question of whether case insensitivity really simplifies things, it's a huge tax, right? I mean, every time you people, I think a lot of languages avoid it in part just because if you build it in, then you're building in paying for it, and so you're always doing some kind of case insensitive hashing, and can't just compare strings.
So does this virtual binding mean that things are faster than before? Because
things are, I mean, faster. The goal wasn't to make things faster. The goal is hopefully to be no slower. There's less, although I do believe in the end it's possible. Well, I'll tell you one thing. For eaches and use statements and such, that had to change the binding, we have to make copies. I told you like make object didn't make a copy.
Mm.
I'm trying to remember. Did use make a copy? I think it did. You can test that in an interpreter if you want. Just have a block, put some binding, bind it, and then use, and then put it on it and see if it corrupts your bindings from your original block. But while loops didn't copy their bodies, and I'm thinking, hey, wouldn't it be neat if breaks and continues could remember and know and be specifically bound to the loop that they break or continue? So then you wouldn't have to worry about, it'd be like the return situation. In order to do that, we would create a little object. Maybe we'd only create the object if you used a break or continue in the body. I don't know. But create a little object that has break continue, and then virtually bind the body to that. And so then you wouldn't have, it would always break from the right conceptual place. And that's a neat idea. But when you think about a while with a for each, with a so-and-so, and then each loop through, you're doing a deep copy of the body and binding it. That's going to be taking a lot of space for the copies and having to GC those copies and a lot of time. The virtual binds I showed you, it's just each time it's one little 8-pointer node. Each time you do a virtual bind, that's your GC cost. Except for the chains, if it makes a new chain. So I try on all these, there are other, it's more complicated than I showed you. That's just sort of a top level way to think about it, but it has to take into account other aspects. And I try to make it copy chains as rarely as it can. So the overhead really is trying to say that each time you add another layer, you're really only paying 8 pointers in a little doodad in a linked list. And most of the time, that's all you do. Now, if your loop body is short, if you say while X, it may be that there are historical, that could be an optimization that we put in there, which is to say that it can be cheaper to copy sometimes, but the copy doesn't have the property that if you modified the original and added elements that it would grow. So anyway, long-winded answer to your question. The goal of this was not to be faster, and it's going to be a little bit hard to be faster than copying and binding a new body for small bodies. But it's a different thing
if you pushed it to WASM.
Yeah, it
like
it runs about as the speed. It hasn't really been optimized because I don't see the point in micro optimizing something that hasn't really been getting. I want to see it tested, and I want to see breaking cases. I have a breaking case, and I don't know what's going on with it, but it's not like common. Most things seem to work. I would love it if people threw really hard things at it and go, well, can it do this? And I go, if you break it, then I want to see it. But yeah, it's not so much designed to perform on current situations better, so much as like orders of magnitude. If you've seen or remember that example I give of making objects, there's the other binding question of when you make an object, having to make copies of all the methods in that object and rebind, deep copy all the methods in the object and rebind it to the instance, which doesn't sound like a very viable way to build a language, right? And so we address that using a similar mechanism to virtual binding. And so I have a demo which builds up some super huge objects with tons of methods, and then it shows how you can make 10,000 of those objects run over their 100 methods each and do this operation that would kills R3 alpha, kills red easily. But we just go doop, 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 and it runs. And so what virtual binding is it's kind of shooting for that big order of magnitude question. The problem with worrying too much about this performance in the small and micro optimizing it on the cases we see now is that we don't have any particularly interesting pathological cases to study, but we could make one by like what I propose, which is to say, let's virtual bind every loop. Let's virtual bind every while loop so that it has a break and continue that's specific to that while. Let's virtual bind every, until, and I just haven't gotten around to trying it, but I think that, when I do, I expect it to handle it pretty reasonably, and I think that'll be a neat feature, and that's something that other languages just don't really have, because they don't, if we've got this, if this is the whole pitch of the language, then why not say that while, there's a sort of gleefulness sometimes if you go read like the red people and like, there is no spoon, you can reduce XXX and in a block, and every X is actually different. And then people go, whoa, that sounds weird or whatever. Well, if you're going to have something that's that weird, it seems that, shouldn't situations like a break, it'd say, and every break is different. That break knows which while or which until or which for each. Then you're starting to talk about something that's actually kind of interesting, right? And so virtual binding is intended to make those kind of more pathological situations of a virtual bind inside a virtual bind inside a virtual bind only add like one little linked list node each time. And yes, you're paying more for the lookups, but I'm looking at ways to sort of optimize these cases, and that's the end goal. So how much faster or slower is it? It's not. It's faster than it was. I think Ren-C. I made a little test and compared it to R3 Alpha, but I didn't like compare it to Ren-C before the change. I don't know how interesting that is necessarily. Just the speed checks are largely, the main interesting thing to me is it slow, and if it's not, then good enough to keep working with it and see. I want to see if there's any technical problems with it. I've got 4 people who've gone to letters here. Can't hear Graham.
I've got everybody on video, so it must be your connection. Okay. So I was just wondering whether this would help Atronics's GUI. That's all.
No. I think that there. My impression is that it's probably the case with any of these big industrial systems that I think people come in and they go like, oh, this would be much easier if we wrote it in X, and then that neglects the fact that there's a lot of edge cases, all these different control systems. So they're probably going to be in maintenance mode for some time. And, if there's ever a big transition, it would probably be buying some competitor and then using their thing instead, or something like that. I don't think that their main concern is so much performance of for loops or for eaches. Where this, I will say one thing that it hasn't really resolved is I was wondering if local variables could be done this way, that you could very dynamically create, and you can. I mean, use is now going to be, I would say it's going to be in the average case more efficient than it was. One area that I do think it's going to be helpful for are lambdas. I think lambdas are basically going to use virtual binding, which means that creating a lambda will be very fast. You just say, here's the variable lambda, here's the block, and no matter how big the block is, you just say, oh, I'm going to use that block and virtual bind it. So you don't, in the process of creating a function, you pay for this copy of the block, you relativize it, you do all these things to it. The vision I have for lambdas is that you don't copy the block, you don't relativize it. You just say, it's just basically a use statement for a small optimized function that then relativizes that variable or a couple of variables across the body. So creating a lambda would be very inexpensive, and you're only usually going to run them once. So you would say to people, hey, if you want to create a function and pay the cost of creating a function and have all the benefits of functions like a return statement and all these things, then do that. But if you want just a quick thing to pass as a parameter as a branch in an if or something, then use a Lambda. And if you don't run it, it won't cost you much of anything. So that's an interesting application of virtual binds, because I think that almost by definition, most of the Lambda cases are supposed to just be run once for that created Lambda. We don't, and if we just avoid using them to create top level functions that we expect to be faster. But for locals, I don't, this let thing is kind of driving me a little crazy. I don't like it. I definitely don't like the idea of searching the body for set words and then making every set word you see in the body a local. That's got too many downsides when we're trying to push the idea that you're using all the parts in the box as your tool set. And now we're introducing this overhead of saying, oh, but be careful using those set words, because if you ever use them, you get local variables. It just doesn't seem like a very safe thing. But then the let thing, the let is better, because instead of tossing out an entire category of part, you've got this one word that you use in the body of functions that signals. And it still has the problem that if you define a function inside of a function, there's no way to see that the inner one belongs to the inner function, the outer one belongs to the outer function, because you're not supposed to look. That walking process isn't supposed to look, and it can't tell what's a function or not, because what if you rename func? It can't tell. So you've got that liability, but it's still not as bad as the set words. But some of the tricks I was thinking about, where a let statement introduces a virtual bind that kind of follows along for all the evaluations that come after it, it's possible. We can't do that. It's a little sucky though, because I imagine writing things like while loops that would, if you introduce a let or something, you would have to take the binding that came out of the condition block and then apply that to the body block. Because if I declared a let inside the condition, I want that variable to be visible inside the body of the while, right? Makes sense to me. Otherwise, you have to put your let outside the while so it can be seen by both blocks, which is a very C-like concept. So virtual binding hasn't really come in and said like, oh, we have this super winner, super fast way of doing things that's good enough for declaring granular one variable at a time in your function things. But I don't know that yet. I don't know that it's reached its end or its limit. It's only just started, and so I'd kind of like to know if it has any bugs. Like I say, I have one scenario. I'm just not looking at it today, but it's sitting there for me to look at and figure out where it's going wrong. It's creating a circularly linked list of patches. So I have to figure out why it did that. I prefer smaller examples, but it's a very large example.
So Chris, you got lots of libraries. You should be trying this all out.
Try it on. It seems to work on everything I tried except for that one thing, which is the entire process of source analysis, which is Brett's. It's all parse. It's parse related. The biggest problem. So one thing that virtual binding changed. It builds on the same mechanics that derived binding and stuff work on, which uses these specifiers for frames. And but specifiers had this nice property, which is that when you make a function and it walks down the body of the function, it marks every block with a little pointer to the function that says, hey, I am a block relativized to that function. And every word it's binding, it says, hey, I am a word relativized to that function. And so then you have this nice debug check whenever you're trying to plug together a frame with a relativized word. You go, are they compatible? If you try to do it twice, it goes, hey, I've already resolved it. you don't need to apply a binding resolution to this because this relative word is already known. It's been combined with a frame. So you catch yourself when you do it twice. Virtual binding doesn't have that luxury because any resolved value that is resolved completely looks like it's finished, but you know that it hasn't been bound. But the problem is that if you have something that before would say, hey, I get a relative value, now I'm going to specify it with a binding, yay, you could then go to try to apply it again and say, okay, I'm going to specify it. Go, oh, it's already specified. With virtual binds, you end up applying things twice. You can, because there's no type checking to say whether something has been or hasn't, because it can happen an arbitrary number of times. And parse was doing it twice, and I'm sure it's probably pertaining to something like that, where it's using the same chain twice without knowing that it's doing it. And I don't know. I mean, so if something you could catch it, here you have a chain, and then you add a thing on top of it, and then unknowingly, even though you've already resolved it, you add this one again, and so you end up in a loop. So I don't know. There's at least one bug. I'm sure there are more. But it would be very helpful if people tried to confuse it. Just come up with something, use and a function, and compose and ask, did it do what you expected? So I don't know. Do people find it at all exciting to think about the idea of every while loop and every for each having a different continue and break so that they know and they actually jump to the right one? Or is that not compelling? I think it's necessary. I think it's as necessary as the returns are, because when you think about the meanings that you have at source level, the user who writes break at source level.
Will it help your debugger?
I don't know. Probably not. Probably not. But the thing is that if you write code in a style that the things that you're using iterate, it's hard. You don't know exactly which thing is breaking, but there's one thing that we do need, which is to know when something is leaving a scope and jumping past it, so you can clean up. And that's it doesn't matter why. It can be a return, it can be a break, but if something is crossing you, you need a way to clean up. And so we don't really have great answers for that. Very few people do. But I don't know. The virtual binding thing is just something that has bothered me. It got more and more bothersome when you're trying to implement a feature like the protect. You need to be able to trust that things aren't being mutated without you knowing it. Otherwise, your protect is toothless, or const, which is the difference between like protecting and const is whether it operates on a series or whether it operates on the cell. So operating on the cell is removable, and then some things freeze, so you can't ever change them back. Some things are flippable on and off. I don't know, but if we can't trust it, then features like those aren't going to work. And should you just let things mutate the bindings out from under everything? I don't think that's good. And because people don't do anything sophisticated, it's very rare that people were doing anything sophisticated with binding. And I think that's bad. I think it just kind of shows that the language was being used at a very surface level, like an app. And I keep saying this, that you can make an app that has some scriptability, but that's really under the pitch of what Rebel seemed to want to sell, which is that you really can design your own things and you can manipulate this and it's powerful. But I think that a lot of people were using Rebel as like, hey, Carl, we want our you're our consultant. Tweak our tool so that it can do this thing number 14 that's interesting to us. And the real value there was his time. The value was being a consultant and engineering that solution, and being willing to do it for your audience, which isn't quite the same, as customizing an app as opposed to really giving people a language that holds up for composition that they do on their own time. And binding is critical to that.
So everybody should run their code and see what happens.
Hey, thanks for that. That was really interesting, but I do not claim to understand everything you've said by a long shot. The one thing I was thinking is, whenever I get stuck with questions around binding, I always go back to Ladislav's Bindology article. So would it be useful for me to run through all the examples of that and actually have a play with that and see if I can come up with anything useful that breaks from that?
Yeah, well, I mean, if you can come up with anything, the main thing to notice about virtual binding is just that it overrides whatever the mutable binding that's in that cell is for anyone looking at it through that virtual binding view. And that's the idea of it, right? So if you use X and then you or in the in operator is what I took, although I did talk about whether or not in is a good name for a operator when it might be more like a variable for in and out. But you can say, hey, I want to take this code and I want to see it from the perspective of if it were bound into this object, but I don't want to change it. And that's what in does right now. So if you take all of Vladislaw's examples that use mutable binding, for the most part, a difference you would see is that you should be able to have to not see any change. Well, first of all, to not see any change to your original data. So if you ever found it so that you ran a virtual bind on something, and then the code that you gave the virtual bind, the in operator, ran differently, that's a bug. It should have all the same bindings, and it should